Let's look at a example problem in 7.2 where I give you the model and it's actually with E instead. So a lot of the problems that are in this section, we have like some A constant and maybe you have to solve for it or something. And it's like, the rabbit example was like 2.4 to the T. That's not how most applications of exponential functions are done. Most of them are going to be with an E instead. So it'll be E to the, something T. And your growth or decay is going to be determined by the coefficient in front of the T inside of your E. So if this thing is positive, then you have E to larger and larger numbers and you're growing. Or if this thing is negative, then you have 1 over E so that it's decaying, right? So this is really what your growth and decay models are going to look like in actual applications. Okay, so the population of a certain town is given by this model, 23,219 times e to the negative 0.01 t, where t is years since 2007. So what is the population of the town in 2009 and 2007, and then what is the population in 2009 and 2011? So when I see this, I see that I have a negative inside of my exponential, meaning it's going to be getting smaller as time goes on, and the coefficient there, the constant, is 0.01, which is 1%. So I'd want to see a 1% decrease every year, something like that, right? All right, so what's the population of the town in 2007? Now remember that T is years since 2007. So in 2007, how many years has it been since 2007? 0. So really this is asking for what is the initial population. Now we know that this number, 23,219, is the initial population. But suppose you don't. Initial means at the start. So suppose you don't realize that it's going to be that 23, and you go ahead and you try and solve for it. All right. So we want t to be equal to 0. So that means in my machine, I'm plugging in the number 0. This machine takes in years since 2007 and spits out population of town. Misspelled years. Okay, so years since 07 goes in, out comes the population of the town. All right, so P of 0 is 23,219 times e to the negative 0.01 times 0, which is 23,219 times e to the 0. But remember that anything to the 0th power is 1. So this is just 23,219. All right. So this, by the way, is why that coefficient in front, that constant, is called the initial population, because if you plug in initial time, t equals 0, the exponential stuff goes away, and that's always true of all of our exponential expressions. All right, so B, what's the population in 2009 and then in 2011? So in 2009, t equals 2, because 2009 is 2 years since 2007. So in goes 2. and out is going to come my population. Now, of course, I'm going to have to use a calculator for this. So here's a calculator. On this one, I am able to just input it as it is written on my paper. The E button usually is like attached with the, this looks like IN, it's LN. This is the natural logarithm we're going to talk about in the next section. So this is usually where E is attached. If it's like on mine where it's not on the button itself, but it's like above the button and in a different color, so on mine it's orange, which I'm not sure how well you can tell, but there's usually a shift or second button that you're going to have to hit first then. So I hit that and then the E, and I need negative 0.01 times 2. I could also put in just E to the negative 0.02. Alright, so that's 22759.23. So 22759.23, which when I round to the nearest whole person is 22,759. Now when I look at 2011, T equals 4. So same comment here as on the last video. Just because I decreased by 1,000 people from 0 to 2 years doesn't mean that I also decrease by another 1,000 people, because that's an assumption that this is linear. So I'm not going to see that it's just the same number difference, right? Okay, so in goes 4. So P of 4 is 23,219 times e to the negative 0.01 times 4. All right, so bust out your calculator. 23219 times e to the negative 0.01 times 4. So 22308. All right, so approximately 22,309. So see, as I have gone on, it's decreased actually by less, because I have, if I'm doing roughly a 1% decrease every time, every year, well, 1% from here to here is more. The 1% of this initial is more than the 1% when I'm measuring from years 2 and 3. So actually less people are going to be having overall left my town. All right. Let's actually compare. So from 0 to 2 years, I lost 406 people. So that's the 23219 minus 22759. And then from 2 to 4 years, I only lost, so I should lose slightly less people. I lose 450, so 10 less people in the second 2 years. So 22759 minus 22309, that's only a difference of 450. So slightly less people left in those second 2 years. So again, you cannot use the fact, you can't pretend like this has linear growth. It doesn't have linear growth or decay.